First, aluminium oxide coating can provide adhesion promoter. Wire cut is one of the typical failure mechanisms of high-reliability packages. Because of thermal expansion and hygrol expansion, debonding occurs between the wires and encapsulation. This is an interfacial fracture between the wires and encapsulation. This interfacial cracks grow long enough. And then, wire cut occurs because, at the end of day, it is the wire alone that has to carry all of the thermal stresses and hygrol stresses without help of EMC. Typical solution of the customers is to increase the wire diameter, because the bigger wires can carry bigger stresses. On your right-hand side, aluminium oxide coating on conventional bond wires can provide adhesion promoter. So, aluminium oxide can prevent interfacial cracking or fracture between the wires and EMC. So, aluminium oxide coating can prevent wire cut failure. Package-level reliability testing was done for high-reliability packages susceptible to wire cut failure during accelerated thermal cycling. Very serious temperature swing from -65 to 150 degrees Celsius. Bare gold wire started to fail at 1400 cycles. Aluminium oxide-coated wire survived more than 2000 thermal cycles. Please note that the diameter of aluminium oxide-coated gold wire was much smaller than bare gold wire cases. 1.2 mil and 1.5 mil also survived at the end of 2000 thermal cycles. This indicates cost reduction is possible by making use of aluminium oxide coating on gold wires. Next, passivation for CU wires, left-hand side. Conventional copper wires, at the end of one day, very severe copper oxidation occurred. When we applied aluminium oxide coating in 8 days, we did not observe any color change of the wires. Minimum aluminium oxide thickness was found 8 nanometers at 250 degrees Celsius for 8 days. On the top of package applications, aluminium oxide-coated wire can be applied to coil applications as well, like inductors, voice coils and so on. Automatic wire bonder was modified for providing winding capability. Wire winding was demonstrated for 180, 330, 1200, 4000 micrometer cores using aluminium oxide-coated wires. At the bottom, inductance was measured out of the winding. Good relationship was found between the inductance and the number of windings squared. The equation is shown on right-hand side. OCB was found very sensitive to aluminium oxide coating thickness. Two different wire diameters were used, 0.7 mil and 1.1 mil. Two different wire metals were used, gold and silver. No OCB for gold wire greater than 1 mil if aluminium oxide thickness is smaller than 10 nanometer. 0.7 mil gold wires. Aluminium oxide coating thickness should be 5 to 7 nanometer for OCB prevention. Next one is 0.7 mil wire diameter. For aluminium oxide thickness greater than 10 nanometer or so, OCB begins to break out at a large scale. We demonstrated 20,000 continuous bonding operations. No problem. 0.7 mil gold was used. Aluminium oxide coating thickness was 6 nanometer. At last, we came up with OCB ranking. Gold is the best. For the case of silver wires, aluminium oxide coating improved OCB performances for both yes N2 and no N2 cases. Here I am gonna explain why OCB is affected by oxide thickness. During ball formation, the neighboring wire gets very hot. This neighboring wire, I would call it as TBMZ. Even during a very short period of time, the surface of TBMZ experiences oxidation. This oxide thickness depends upon a wire material type. If this TBMZ oxide thickness is small and thin, no OCB problem. If this TBMZ oxide gets thick, it does not break down gradually during ball formation. Rather than that, for instance, left-hand side oxide layer is not broken yet, but right-hand side oxide is broken already. As a result, there is no more symmetry or axisymmetry. This triggers tilting the molten ball, or a formation of OCB. For example, silver and copper experience thicker oxide layers. so they are more susceptible to oxidation of TBMZ or OCB formation. So, if we can control the oxide thickness of the TBMZ by making use of our aluminium oxide coating, we can prevent OCB problem, especially for silver and copper wires. Here, 1.1 mil gold wire having the aluminium oxide, 6 and 8 nanometer. Fab size is same. Bonded ball size is same. Bonded ball height is same for 0. 6 and 8 nanometer thickness aluminium oxide coating on gold wires. We found strength same as well. Wire pull strength, ball shear strength, stitch pull strength. There is a small drop, but stitch fracture is found same. Here, wire diameter is 0.7 mil gold and silver wire. Almost same strength data were obtained. Aluminium oxide coating does not change IMC types or IMC thickness between wire and pad metals. The resulting IMC surrounds the broken pieces of aluminium oxide. And aluminium oxide has a good adhesion to wire and pad metals. That is why bonding strength is the same for both no coating and coating cases.